Now that we've gotten plenty of practice with the negative exponent rule and integer exponents, let's talk about rational exponents. So here we have a to the 1 over n. And what we say is that a to the 1 over n is the nth root of a. A to the 1 over n is the nth root of a. Notice that a to the 1 over n raised to the n power, if we apply the power rule here, that would give us a to the n over n. And of course, n over n just simplifies to 1, so that's going to equal just a to the first. So that tells us that a to the 1 over n is a number whose nth power is a. So we can say a to the 1 over n is the nth root of a, but that just means that it's a number whose nth power is a. This will be easier to think about when we get some numbers in here. So let's practice. Here we have 36 to the 1/2 power. So what this means is we're looking for the number whose second power is 36. A number whose second power is 36, and of course that number is 6. And on part B, we have 8 to the 1/3. So we're looking for a number whose third power is 8. And of course that number is 2, because 2 times 2 times 2 is 8. Now what if the base is negative? Well, if the base is negative, then the result depends on whether we're finding an even root or an odd root. Remember that a negative times itself gives a positive result. So a negative number that's raised to an even power is also going to give a positive result. So with that in mind, think about the problem negative 25 to the 1/2 power. So in this case, we would be looking for a number whose second power is negative 25. But that doesn't make sense, because if you square a number, you get a positive. There aren't any real numbers whose second power is negative 25. Any number times itself would give a positive result. So, if a is negative, if your base is negative, but the denominator of your exponent is even, for right now we're just going to have to say that a to the 1 over n is not real. For example, negative 16 to the 1/4 power is not real, because in this case we would be looking for a number whose fourth power is negative 16. But any real number raised to the fourth power is going to have to be a positive, so this is not a thing we can do at this point. So let me try to bottom line this for you and give you just some guidelines to go by. If the denominator of your exponent is even and a is positive, the base is positive, then a to the 1 over n is the positive nth root of a. So for example, something like 49 to the 1/2 power is 7, because we're looking for a number whose second power is 49. So of course that's 7. If n is even and a is negative, then a to the 1 over n is not real. So for example, if we had negative 49 to the 1/2 power, that would be not real, because in this case we would be looking for a number whose second power is negative 49, and that's not possible using real numbers. So we would just say not real. So just to recap so far, if the base is positive and the denominator of the exponent is even, go right ahead. If the base is negative and the denominator of the exponent is even, then you got to say that that is not real. But if n is odd and a is any non-zero number, then a to the 1 over n will either be positive or negative nth root of a, depending on whether a was positive or negative. So if the denominator of your exponent is odd, then everything's fine. You can just go right ahead. So for example, if we had 125 to the 1/3 power, well, we're looking for a number whose third power is 125. So of course that number is 5. And if we have negative 125 to the 1/3 power, we're looking for a number whose third power is negative 125. And of course that number is negative 5, no problem. So as long as the denominator of your exponent is odd, then your result will either be positive or negative, depending on whether the base was positive or negative. The only time we run into a problem is if we're doing the even root of a negative number, because the even power of any number is going to be positive, so you can't do the even root of a negative number. All right, so now let's practice a little bit. So we're going to evaluate each of these. Here we're looking for 36 to the 1/2 power. We've looked at this one before. We're looking for a number whose second power is 36, so of course that is 6. In part B, we have negative 100 to the 1/2 power. Now be careful about what your exponent is applying to. Here, the 1/2 power is applying to the 100, but there are no parentheses, so the exponent is not applying to this negative right here. Okay, so the negative is going to sit in front of the answer, and then we're looking for a number whose second power is 100, so of course that number is 10. So negative 100 to the 1/2 power is negative 10. In part C, we have in parentheses negative 225 to the 1/2 power. So in this case, we're looking for a number whose second power is negative 225. Because of the parentheses, the exponent is affecting the negative. The problem is any number that's squared is going to be positive, so there are no real numbers whose second power is negative 225, and so this result would be not real. And in part D, we're doing the even root of a positive number, so that's fine. In this case, we're looking for a number whose fourth power is 625. Now, if you think about it, 625 is 25 times 25, so that's 5 squared times 5 squared. So 5 to the fourth is 625. So we can say that 625 to the 1/4 power is 5. Here are a few more to practice on. Same example. So we're just evaluating each expression. Negative 1296 in parentheses, all to the 1/4 power. See, we're looking for a number whose fourth power is negative 1296, but that's not possible with real numbers, so we're just going to say that's not real. In part F, we have almost the same problem but without the parentheses. And remember that without the parentheses, the exponent is not applying to the negative. So here we have negative 1296 to the 1/4 power. So we're looking for the negative of a number whose fourth power would be 1296. So let's start by just trying to break this number down. With a little trial and error on your calculator, you can figure out that 1296 is 36 times 36, and of course each of these is 6 to the second power. So this 36 gives you 6 times 6, and so does this one. So now we know that 1296 is 6 times 6 times 6 times 6. In other words, 1296 is 6 to the 4th power. So the number whose fourth power is 1296 is 6. So now we can say that negative 1296 to the 1/4 power is going to be negative 6. And that's our final result. Now let's look at part G. Here we have in parentheses negative 27 to the 1/3 power. Now think back to part E for just a second. Remember over here we were looking for the fourth root of a negative number. So we said we're looking for a number whose fourth power is a negative. And we said that that was not possible with real numbers because the fourth power of a real number will come out positive. That's because 4 is an even number. When you multiply two negatives together, you get a positive. Over here, we're looking for the odd root of a negative number. And the odd power of a negative is negative. So again, it is possible to find the odd root of a negative number because a negative number raised to an odd power will give a negative result. So we can just simply say here that we're looking for a number whose third power is negative 27, and of course that number is going to be negative itself. So we know that 3 times 3 times 3 would be 27, and we know that negative 3 times negative 3 times negative 3 would be negative 27. So the number whose third power is negative 27 is just negative 3. And then on part H, we're asked to find negative 32 to the 1/5 power. And this time we don't have parentheses, so remember the negative is just going to sit in front. So we're looking for the negative of the number whose 5th power is 32. Well, if you think about it for just a minute, you'll realize that 2 times 2 times 2 times 2 times 2 gives you 32. So the number whose 5th power is 32 is going to be 2. So if we're looking for negative 32 to the 1/5, that's going to be negative 2. Now, what if the top number of the exponent is not 1? What if the top number of the exponent is some other number? Well, let's let m be any integer and n be any positive integer. So if m is negative, it'll make the whole exponent negative. If m is positive, it'll make the whole exponent positive. And let a be any real number for which a to the 1 over n is real. So in other words, we don't want to worry about what would happen in a situation where the answer is not real right now. So if you have a to the m over n, you can rewrite it this way. You can think of it as a to the 1 over n, all raised to the m power. So notice that 1 over n times m would be m over n. So you can always separate a to the m over n into two separate exponents. A to the 1 over n raised to the m power. So anytime you want to mentally evaluate a rational power, first use the denominator of the power to find the required root, and then apply the outside exponent to find the required power. Let's practice doing that. If you've got a calculator in your hand, yes, the calculators will do these exponents, but you have to still know what you're doing. So I want to really encourage you not to use a calculator at this point. You can use it later when you understand the rules better. But right now, let's just practice using the rule we just learned. So 125 to the 2/3 power can be written as 125 to the 1/3 power, all raised to the 2nd power. So you see how 1/3 times 2 would be 2/3. So we've separated the exponent into two pieces because we're able to do the inside piece, and then we can apply the 2 later. So first, let's find a number whose 3rd power is 125. So we're looking for the 3rd root of 125, and of course that number is 5. So this problem then becomes 5 to the 2nd power, which we know is 25. So see how you break it down into two steps? First you do the root, then you do the power. Let's try that again. So here we have 32 to the 7/5. So I'm going to break this down into 32 to the 1/5 raised to the 7th. Okay, now what is a number whose 5th power is 32? Well, that number would be 2. So this problem then becomes 2 to the 7th, which we can work out. You might not know this one off the top of your head, but I'm going to write it down long way and we'll figure it out. Here you have 2 times 2 times 2 times 2 times 2 times 2 times 2, so 7 of them. 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times another 2 gives us 32, times another 2 gives us 64, times this last 2 gives us 128. So the final answer here is 128. Now for part C, we have negative 81 to the 3/2 power. And remember, there are no parentheses here, so this negative is not being affected by the exponent. It's just going to sit in front of the number. Okay, so first, let's separate this into two pieces. Here I have the negative outside the parentheses, and I have 81 to the 1/2 power, and then I'm going to raise that to the 3rd power. And again, the reason the negative is out here instead of in here is because the original problem did not have parentheses. So let's go ahead and evaluate 81 to the 1/2 power. So we're looking for a number whose 2nd power is 81. Of course, that number is 9. So now that gives me negative 9 to the 3rd power. Okay, 9 to the 3rd power would be 9 times 9 times 9. Now if we write that out long ways, it would look like this. this negative is not being affected by the exponent. So we have negative 9 times 9 times 9, and we can work that out. 9 times 9 is 81, and then 81 times this 9 is going to be 729. So the overall final result is negative 729. Here are a few more to practice on, same example. So here we have negative 27 in parentheses to the 2/3 power. So of course we want to split this up, and because the negative is inside the parentheses, it's going to stay there. So it's going to be negative 27 in parentheses to the 1/3 power raised to the 2nd power. So here you see the parentheses and the brackets because I needed to use the parentheses to keep that negative in there, and then because I'd already used the parentheses, I used brackets out here. Alright, now what is a number whose 3rd power would be negative 27? Well, that number would be negative 3. Think about it. Negative 3 times negative 3 times negative 3 would give you negative 27. So inside the bracket, I'm just going to have negative 3, and then I'm going to square that, and negative 3 times negative 3 would be positive 9. Here in part E, we have 16 to the negative 3/4, and we know that we always need to make our exponents positive before we start working on anything. So I'm going to write this as 1 over 16 to the 3/4. And now I can separate this into two separate exponents. So it's going to be 1 over 16 to the 1/4 all raised to the 3rd. Now, what is a number whose 4th power is 16? Well, that number would be 2. So this becomes 1 over 2 to the 3rd. And of course, 2 to the 3rd is 8. So this becomes 1 over 8. And then finally, part F, here we have negative 4 in parentheses, all raised to the 5/2 power. Okay, so we know how to split this up. It would be negative 4 in parentheses to the 1/2 power, and then all raised to the 5th power. So the first thing we have to do is figure out what is a number whose 2nd power is negative 4. Well, we're not going to be able to find a number like that because any number's 2nd power is going to be positive. There is not a real number whose 2nd power is negative 4, and so we can't get any further than this, and we'll just have to say that this one is not real. Now that you know how to use rational exponents and what they mean, you need to know that all the exponent rules you've already learned still apply when you're working with rational exponents. You still can use the product rule. A to the r times a to the s would just be a to the r plus s. You still can use the quotient rule. You just subtract exponents. You still can use the negative exponent rule and all the power rules. All the rules still work. But anytime you're working with exponents, always make sure that you leave your answer so that all exponents are positive. Never leave negative exponents in your final answer. Okay, let's get a little practice here with example 6. It says simplify each expression and assume all variables represent positive real numbers. So don't worry about what would happen if a variable was negative. We just can pretend they're all positive. Okay, here in part A, we have 27 to the 1/3 times 27 to the 5/3 all over 27 to the 3rd. Now, of course, you could go ahead and evaluate each one of these, but it's usually easier to let the exponents do most of the work and then evaluate at the end. So first, let's use our product rule to add these two exponents together. We have the same base, so if we can just figure out 1/3 plus 5/3, we can do this multiplying. Well, you know 1/3 plus 5/3 is going to be 6/3, and then in the denominator we still have 27 to the 3rd power. Now this exponent can be simplified. 6 over 3 reduces to 2. So that gives us 27 to the 2nd power over 27 to the 3rd power. And now we can use our quotient rule. When the bases are the same in a division problem, we can just subtract the exponents. Remember, I've taught you to always start with the larger exponent and subtract the smaller one so you get a positive answer, but then your answer is going to go where the larger one was. So 3 minus 2 is 1. But you can see that I had more 27s in the denominator than in the top. So the leftover 27 is going to be in the bottom, and that's going to give us 1 over 27 to the 1st power, which is just 1 over 27. Now in part B we have 81 to the 5/4 power times 4 to the negative 3/2 power. Here we cannot just add these exponents because the bases are not the same. But what we can do is get rid of this negative exponent and then simplify. So we're going to have 81 to the 5/4 over 4 to the positive 3/2. You see how moving that 4 to the negative 3/2 down to the denominator made that exponent positive. Okay, now let's write each of these in our form where we have two exponents. So we're going to take each of these exponents apart. For the top, we're going to have 81 to the 1/4 all raised to the 5th. And for the bottom, we're going to have 4 to the 1/2 all raised to the 3rd. Now each of these is going to be pretty easy to evaluate. A number whose 4th power is 81, that's going to be 3. So the top is going to be 3 to the 5th. And in the bottom, a number whose 2nd power is 4, well, that's going to be 2. So in the bottom, we're going to have 2 to the 3rd. All right, now we can work this out. 3 to the 5th would just be 3 times 3 times 3 times 3 times 3. I'm going to let you work that out on your own. I'm going to go ahead and tell you that 3 to the 5th would be 243. And then in the denominator, 2 to the 3rd would be 2 times 2 times 2, so that's 8. Now, if this could be reduced, we would need to reduce it, but the top is all made of factors of 3, and the bottom is all factors of 2, so there's nothing here that will reduce. And here on part C, we have 6y to the 2/3 times 2y to the 1/2. So this one actually is pretty easy. All we need to do is multiply the coefficients together, and then we can think about how to multiply the y's together. So 6 times 2 is going to be 12, and then we'll have y to the 2/3 times y to the 1/2. Now, this is a place where we can apply the product rule for exponents. So you can see that I have y to a power times y to a power. That means I need to add the exponents. So I'm going to need to add 2/3 plus 1/2. And since we're adding fractions, we're going to need common denominators. Now you can look at this and see that the common denominator needs to be 6. 6 is the smallest number that 3 and 2 can both go into. So what would I have to multiply this fraction by to get a 6 in the denominator? Well, I would need to do times 2 over 2 to make the denominator become 6. So if I do times 2 in the top and times 2 in the bottom, this first fraction is going to become 4 over 6. And then for the second fraction, I need to multiply the denominator by 3. So I need to do times 3 in the top and times 3 in the bottom. So this one is going to become 3/6. Now 4/6 plus 3/6 is going to be 7/6. So our final answer here is going to be 12 times y to the 7/6 power. And we've just got a couple more parts on this example. So here I have 3m to the 5/6 over y to the 3/4 all squared times 8y to the 3rd over m to the 6th all raised to the 2/3 power. Now I think you can look inside each parentheses and see that inside the parentheses there's nothing to simplify. So for each one of these we're going to go ahead and apply the outside exponent. So for this first fraction, that's going to give me 3 to the 2nd times m to the 5/6 to the 2nd, and in the denominator y to the 3/4 to the 2nd. For the second fraction, I'm going to go ahead and have 8 to the 2/3 times y to the 3rd to the 2/3, and in the denominator m to the 6th to the 2/3. Okay, now let's simplify each of these and see where we are. Of course, 3 to the 2nd is going to be 9. M to the 5/6 raised to the 2nd power means we need to multiply these exponents together. So 5 over 6 times 2 is going to be 10 over 6. Now I know that could be reduced, but just leave it for just a minute, and you can reduce it later if you need to. In the denominator, we've got y to the 3/4 raised to the 2nd. So 3/4 times 2 is going to be 6/4. And so in the denominator I have y to the 6/4. Now let's try to simplify these as we go. Here I have 8 to the 2/3 power. Well, we know that we need to do the root first and then the power. So the third root of 8 would be 2. And then 2 to the 2nd power would be 4. We really need to be able to evaluate something like this quickly mentally without having to write down the 2 steps that we used before. Now that you're used to it, maybe you can just do it quickly. So start with the bottom number as the root and then work your way to the power. So we say the third root of 8 is 2, and then 2 to the second power is 4. Here with the y, we have y to the third raised to the 2/3. So we'd be multiplying these exponents, and 3 times 2/3 is going to be 6/3. In the denominator, again, we're multiplying exponents, so m to the 6th raised to the 2/3 becomes m to the 12/3 because 6 times 2 is 12. Now I am going to go ahead and simplify each of these exponents before we take the next step. So 10 and 6 can both be divided by 2. So in the top here, I'm going to have 9m to the 5/3. In the denominator, both the numbers in this exponent can be divided by 2. So in the denominator, I'm going to have y to the 3/2. And then moving over here, 6 divided by 3 is 2. So the top here is going to be 4y to the second power. And in the bottom, 12 divided by 3 is 4. So that's going to give us m to the 4th power. Now we're ready for the last bit where we just need to do this multiplication. The first thing I notice here is that 9 times 4 is 36. So I'm going to go ahead and do that, and I'm going to leave everything else the same. But now it's all in one fraction. So I've got 36 m to the 5/3 times y to the second, all over y to the 3/2 times m to the 4th. Notice that we have m's in both top and bottom, so we'll need to do some subtraction there. And also we have y's in both top and bottom, so we'll need to subtract those exponents. So now the 36 is going to stay, and I'm going to work with the m's first. Notice that the number 4 is larger than 5/3. So when I subtract 4 minus 5/3, the leftover powers of m are going to go in the denominator. So right here, 4 minus 5/3, I need a common denominator, so I'm going to multiply this 4 by 3/3. That's going to give me 12/3 minus 5/3. We know that's 7/3, and we know that because 4 was the larger number, that's going to go in the denominator. So I'm going to have m to the 7/3 in the denominator. Now for the y's, I'm going to do 2 minus 3/2, and I'm going to start with the 2 because it's larger. But again, I need a common denominator. So I'm going to multiply 2 by 2 over 2. So 2 over 2 times 2 would give us 4 over 2. 4 over 2 minus 3 over 2 gives us 1 over 2. And the larger exponent was in the top, so I'm going to have y to the 1 over 2 in the top. And now this one is finished because notice all the exponents are fully combined, and they're all positive, and the coefficients are combined, and that's all we can do here. And then finally on part E, we have m to the 2/3 times m to the 7/3 plus 2m to the 1/3. So this is a place where we would apply the distributive property. So if we distribute, we're going to need to add these exponents. Every time we multiply an m times an m, we need to add their exponents. So to multiply m to the 2/3 times m to the 7/3, I need to add these exponents. 2/3 plus 7/3 would be 9/3. And then I need to do m to the 2/3 times this second term, so I need to add these exponents. Here, m to the 2/3 times 2m to the 1/3 is going to be 2m to the 3/3. Now each of these exponents will reduce. 9 divided by 3 is 3, so that turns out m to the 3rd. And then here, 3 divided by 3 is 1. So with a 1 exponent, we really don't write it, so this will just end up being plus 2m. And that's all there is to that. Notice that we cannot combine like terms here because this is m to the 3rd and this is m to the 1st, so they will not combine. And that's all there is to that one. So don't be intimidated by the rational exponents. You just need a little practice with it, and you need to keep exposing yourself to that over and over. But if you understand the exponent rules that we learned in the previous sections, then just having the exponents turn into fractions doesn't really change anything, except that you might have to do a little adding and subtracting with fractions. But other than that, the rules are all the same.